We're going to start off with a super quick tutorial about how to draw circles on isometric graph paper, and then I'm going to show line by line how to draw this part from these orthographic projections. The 4 holes are going to slightly increase in difficulty, but the final boss is actually going to be the cylinder. Historically, less than 10% of my students get this cylinder correct on the first try, but after watching this video, you'll be able to nail it. Now suppose I'm trying to draw a cylinder extending outwards from all 3 of these visible faces on this cube. When I actually sketch them by hand, circles do not look like circles in isometric view. An isometric view looks more like an ellipse or a rugby football. If these red dots mark the center of your 3 cylinders, then the circles you draw should fit completely within the blue squares, and they should touch the blue squares exactly at the midpoints where these orange dots are drawn. Now, if you're freehanding these without any kind of tool, don't lose too much sleep over a little wiggly line. As long as your circle fits within the blue square and touches the blue square at those midpoints, those 4 orange dots, then you've nailed the most important part. After that, just do your best. For me, the one I drew on the top view is pretty good. That's about as good as I can do it. The one over on the left is kind of wobbly, but I'm gonna go with it. So each of these 3 circles so far represent the base of a cylinder that is gonna be extruded outwards from this box. So suppose this extrusion is gonna come up 5 squares tall. I'll start out by moving the center of the circle out the height of the cylinder there, that 5 squares. After moving the centers, I can add the 4 orange quadrant dots that are just up, down, or diagonal from the center, keeping in mind that which direction they go will be different for each of the 3 faces. Once I add these blue construction lines, you may see the cylinder start to take shape a little bit. And then next step, just draw your orange circles. Again, they have to stay within the blue squares, and they have to touch the blue squares exactly at those midpoints, the orange dots. So now you can erase these blue construction lines, we won't need them anymore. And now the final step is going to be to connect the top to the bottom of the cylinder. And the biggest mistake that students make is going to be trying to connect the quadrants. As you can see looking at the left-hand side, when I connect the quadrants, that does not look quite right. The actual points you need to be connecting are the points furthest in these 2 red directions. And repeat that for the other 2 cylinders. And now the cylinders have taken shape, but what you may be noticing is that a lot of the lines that I've drawn should actually be hidden, which means they shouldn't be visible. You don't draw hidden lines on isometric views. And this is why I drew in orange to simulate being a light line that you might end up erasing later. When finishing up an isometric drawing, you want to draw from top down and front to back and right to left, so that you draw the parts that will be visible first, and then the parts that are hidden, you just avoid having to draw at all. Now, of course, I didn't darken these lines in using a ruler, just a real quick freehand sketch. For all of your drawings, your professor is definitely going to require you to use a ruler so that all of your lines are perfectly straight. So drawing holes is going to be exactly the same as cylinders. You'll start off by drawing 1 circle on your surface, but instead of extending outwards from the surface, you'll extend inwards into the surface. Now, the first step to making any isometric drawing is to give yourself a bounding box to make sure that your drawing will actually fit on your page. So in this case, I have an overall length of 18, a depth of 10, and an overall height of 10.5. And keep in mind that 10.5 isn't given explicitly. You have to add the 9 plus the radius of that outer cylinder up at the top. So when I draw this without scaling, it looks like it fits my page perfectly, but a lot of your problems will require scaling where you may have to multiply or divide all of your dimensions in order to get something that looks right. You want something to take up most of the page and be relatively centered. So I'm going to draw some red dots in my corners since I'm going to use them for reference for measurements, and then go ahead and erase the bounding box since this isn't actually part of the drawing. I just want to make sure things would fit. But if you look at these red dots and think you might lose track of what they represent, then leave the bounding box. You can always erase it later. So isometric drawings is almost always easiest to start with the boxy portions. Anything that has a vertical or horizontal flat surface is going to be easiest to draw first. So for this drawing, we're going to draw the boxy parts first. If you need a refresher on isometric drawings for vertical and horizontal surfaces, click right here. I've got another video covering that topic in much more detail. Open it up in a new tab and then come back to this one when you're done. All right, so we'll do these circles from right to left. It's going to be easiest to hardest. For any hole or cylinder, the first thing is to identify where the center is located. And then since we're given diameter of 1, that means the radius will be half of that, or 0.5. Since this hole is really small, it's going to be kind of hard to draw, but once you've got the center, you can put down 4 dots for the quadrants and draw yourself a bounding box square if you want. And do the best you can to connect those 4 quadrants to each other without going outside of your blue square. And once I erase my construction lines, you've got a hole. Now this hole is small enough that you're not going to be able to see all the way through the part, so you're done. Moving on to hole 2, medium difficulty. This one is going to be large enough that you can see all the way through. So I start off by finding the center of the circle and marking that, going the radius 1.5 outwards in the 4 cardinal directions, and using those midpoints to draw myself a bounding square. Connect the dots, and you've got the start of the next hole. Based on the size of this hole and the very thin piece of metal that it's being cut through, you can see that we should be able to see all the way through this hole, and so we're actually going to draw depth this time. Since this piece of metal has a height of 1, the hole is going to be at a depth of 1, and so I'm first going to start by drawing the center of the circle sunken down a distance 1. From there, I go 1.5 in each of the 4 cardinal directions, and then draw myself a bounding square, where this square is now in the plane of the bottom of the metal surface, not at the top. It's beneath the top hole. As I draw the orange circle by connecting the quadrants, you can now start to see the depth of the hole start to take shape. Erasing the construction lines will help a little bit more. And then once I trace over these lines in black from top to bottom, where I only show the visible lines, then it starts to really take shape. So for the lower surface of the hole, you can only see that section that is visible through the top part of the hole. So continuing right to left to the counterbore hole. Counterbore holes are usually used for bolts so that the top of the bolt can actually sit inside the piece instead of sticking out up above it, so you still have a flat surface on the top. So the way to read this note is that there's a hole in the center of diameter 2 that goes all the way through, that's the smaller hole, and then the counterbore hole, which is the larger one here on the second row, it has a diameter of 3 and only goes down a depth of 1.5. So if we're drawing from the top down, we actually draw the wider counterbore part first, so that's the diameter 3. So once you draw a few circles, you may realize that you don't actually need the square there to be a guide every single time. So in that case, just put some dots for the quadrants and connect the dots. So this wide counterbore section goes down a depth of 1.5, so I move the center of the circle down 1.5. Also has a radius of 1.5, so I can draw 4 dots to represent those quadrants. Based on that second hole that I drew, I know that I only have to draw the part of this lower circle that is inside the top circle. The rest of it's all going to be hidden by the top surface. And in fact, I'll go ahead and darken in that top circle since I know it's not going to be obstructed. Now the hole that goes all the way through, it has diameter of 2 or radius of 1. And so using the same lower sunken in circle that I just used, I'm going to draw a new circle to represent the top part of this inner hole. I drew the whole circle there just for practice, but you see when I darken the line, only this top quadrant that is visible within the top part of the counterbore hole is actually visible. So the counterbore hole looks very similar to the thin hole that you could see all the way through, except now you can see a small flat surface, which is the lip that the top of the bolt would be resting on top of. So last one, hole number 4, the countersunk hole. So countersinks have the same purpose as a counterbore in that they allow a fastener to fit within the part instead of sticking out on top, but the main difference is that they have a sloped side instead of flat. So the note is similar to the counterbore hole. There's a 1.5 diameter hole all the way through, and then the angled portion starts with a diameter of 3 at the top and goes inwards at a 45-degree angle. So I start by finding the center of the top 3-inch diameter hole, and I'll go ahead and draw that as is. So 45-degree angle is probably your best case to draw. You're not even going to use a calculator because it's going to go the same amount down as it does inwards. So since the radius is changing from 1.5 at the top to 0.75 at the bottom for the hole that goes all the way through, that change is going to be 0.75 inwards. So over at a 45-degree angle, that's also a 0.75 downwards. So the top of the inner hole is going to be 0.75 down from the top of the surface. Draw my 4 quadrants and finish out the circle. And I'll go ahead and darken the portions of that circle that are inside the top circle. So the main difference between the countersink and the counterbore is at the counterbore you can see a flat surface where it drastically changes radius immediately, and on the countersink there's a gradual angled change, which means there's one less circle to draw. All right, so now on to the final boss. Now, most students are going to start trying to draw the triangular wedge first, but that's not going to work because you don't actually have dimensions to where the top of the triangle is. So the sloped part of the triangle actually merges tangent to that cylinder, so you have to draw the cylinder first. So we're going to draw 3 circles, one that is flush with the plane of the back half of the triangular wedge, one that's flush with the plane on the front of the triangular wedge, and then one at the very front of the cylinder that's sticking out. I find the center of the circle on the very back side of the triangular wedge using its radius of 1.5. So from that red dot, which is the corner of my bounding box, I go over 1.5 and down 1.5, and that's going to be the center of the circle on the back plane. Or if it's more helpful to see that bounding square, this is what that square looks like that the circle is going to be contained within. The triangular wedge has a depth of 2, so I move my center of the circle in that blue box forward by a distance of 2, and this is going to be where I'll draw the plane of the cylinder that is flush with the front of the triangular wedge. Then the very front of the cylinder is sticking out an additional 3 to give the cylinder a total length of 5. I draw the 3 circles in orange because I'm not sure yet what's going to be visible and what's going to be hidden. But once I have those, you can at least erase the construction lines. And you can draw the straight lines to make the shape of the cylinder. Almost done, just the triangular wedge to go. The triangular wedge is going to go from the bottom edge of that flat section all the way up to the cylinder, and it's going to be drawn tangent to the cylinder, just the same way we drew these straight lines that connect each of the circles in the cylinder. We drew them tangent as well. So I added these red dots to the quadrants of that circle to remind you that the triangular wedge meets tangent to the circle, not at one of the quadrants. It actually hits somewhere in between the quadrants. Since the triangular wedge has a depth of 2, the second line that I drew is just brought forward 2, both on the lower end and at the top end. And you can see on the top end, it meets tangent to that second circle that I drew. So I've darkened in most of the lines that are visible from front to back, top to bottom, and erased more and more construction lines. But the part that nearly every student I teach gets wrong is how to actually finish what's visible on the cylinder on the front face of that triangular wedge. And the answer is that the straight line should only extend to the point where it is tangent to that middle circle. In that middle circle, you should be able to see the curved section up to the tangent of the triangular wedge itself. And now erasing the rest of the construction lines, you can see what that final shape would look like. And looking at it now, it does not look all that complicated. But trust me, I have seen probably 50 different versions of how to draw that connection between the triangle and the cylinder. It is not easy. But the way I drew it, by drawing all 3 circles, the circle on the back half of the wedge, front half of the wedge, and extending out forward, that's the way to ensure you have all of the connections needed. That's the way you ensure that you have all of the correct tangent locations that you need to finish the drawing. So one more hole through the center of that cylinder, and once I drew it, I had to then redraw also the outer circle because it looked so bad. And that's it. So with that, we can just say thank you to your TA Indiana for coming by to help us out with this last step. And if you're in the mood for more isometric drawings, I've got another video up here with an angled surface and a rectangular cutout through the angled surface, which actually makes it pretty challenging. So if you're ready to do a little bit more engineering graphics, watch this video next. That's going to be the best one for you. Thanks for watching and enjoy the rest of your day.